Activity 2. Voltage limiter circuit with a Zener diode. We start with the voltage source, go to a current limiting resistor, a Zener diode, so it has the little things on the symbol, and it's in the reverse bias direction, with the assumption that this is the positive part of the power supply. The diode I'm choosing is a 1N4738, which is a 1 watt diode with an 8.2 volt Zener voltage. The current limiting resistor. For the lab, we will be using the DC power supply, and in keeping with the voltages that we've been using so far with the lab, we're going to base the load resistor on this power supply being 16 volts. 16 volts minus the Zener voltage, with a number limit of 20 milliamps. $390 ohms minimum. Or, if we wanted to limit the current to above 10 milliamps, then the 390 ohm resistor can be as large as 780 ohms. The datasheet for the 1N4738 shows 8.2 volts as the Zener voltage, 31 milliamps as the test current, and up to 110 milliamps if used as a regulator. But we're going to limit it to 20 milliamps, and I want it to be as close to 20 milliamps so that it's as close to the 8.2 volts as possible. Since both of these are non-standard resistors, once again, we can get very, very close by using a 330 ohm resistor in series with a 100 ohm resistor that I do happen to have in my kit, giving us 430 ohms. Being a very simple circuit, I'm going to construct this one very linearly across the board. So we have a 330 ohm resistor on the left, leading to 100 ohm resistor for a total of 430, leading to our Zener diode in line with those. So this time around, I just simply constructed the circuit like this. Now, we will power this by the DC power supply and get some accurate data points, but initially I'm going to put this on the function generator so that we can see it on the scope. Okay, so we have our Zener voltage limiter set up on top of the oscilloscope, and the function generator, which is still putting out positive and negative 10 volts on a sine wave at 60 Hertz, is being shown by oscilloscope channel 1, which is the yellow trace you're seeing at the moment. Channel 2 is connected exclusively across the Zener. If I turn on channel 2, you can very, very clearly see that the positive peak from the function generator that is about 9.75 volts is being limited by the Zener to 7.94 volts. Meanwhile, the negative half cycle, which is causing the Zener diode to conduct in the forward direction, 9.8 volts, is being limited to the forward bias voltage of pretty much exactly 1 volt. So this is the reverse bias, this is the Zener voltage, and this is the normal forward bias diode drop that we're used to seeing on the rectifier. Now, if I change the function generator to give us a triangle waveform and alter the offset and the magnitude so that it's exclusively positive, watch what happens. So, as you can see, the Zener voltage is pretty flat, 7.9 volts, regardless of what we give it from the function generator. We're going to get some more precise numbers from this area right here by using the DC power supply. Channel 2 of the DC power supply, channel 2 display. Channel 2 is functioning as the input to our circuit. The output of the circuit, which is just the voltage across the Zener diode, is being read by our multimeter. Now, don't be fooled by this. Right now it's auto-ranging, and this is millivolts, not whole volts. It's not 1.3 volts, it's 1.3 millivolts. We are going to slowly ramp the supply voltage up towards 16 volts. At key points, I'm going to measure the current and the voltage that is across the Zener diode. So to start, we're at 0 volts, 0 milliamps in, and 0 volts across the Zener diode. When we pop it up by 1/10 of a volt, the Zener voltage is now 1/10 of a volt, 100 millivolts. But you'll see 0 current is flowing. So 0.1 supply, 0.1 Zener, 0 milliamps through the circuit. 0.2, 0.2, 0. 0.3, 0.3, 0. And the voltage across the Zener is going to continue to track the input to the circuit until we reach that point where it begins to conduct. So we'll just stop at 5 volts and take a data point. 5 volts on the supply, 4.88 volts on the Zener, and 0 current. There will be some measurement error between the DC supply through all of the wiring, especially some of the smaller wiring, and my meter has errors as well. So you can remove those errors later. Continue ramping up, 6 volts, 5.86, and 0 milliamps. Seven, 684, and 0 milliamps. And we are getting close to the Zener, so an important place where I'm going to stop and take a measurement is as soon as I see that first milliamp show up as a continuous current through the circuit. 8 volts in, 7.8 on the Zener, and 0 milliamps. And we should see it begin to conduct anytime. There we go. So our first milliamp of supply current is at 8.3 volts input, and the Zener is 7.88. Now I will get 2 milliamps, and I will get 2 milliamps at 8.8 volts, 2 milliamps, and 7.91 on the Zener. Three milliamps at 9.3 volts, 7.94 on the Zener. (9.8), 4 milliamps, 7.95 volts. Let's accelerate this a little bit, and we'll go to 6 milliamps. At 10.7 volts, and 7.98 on the Zener. Now, it does seem somewhat linear. It doesn't seem to be taking off. So I'm going to take 11 volts, 12, 13, 14, 15, 16. At 11, 6 milliamps, and 7.99 volts. 12. 13. 16 volts. Topping out at 18 milliamps, 2 milliamps away from our 20 milliamp max for these laps. And the Zener is 8.13 volts. Now let's put this in Excel and plot it. So after entering all the data and plotting the chart, I did decide to remove one data point, and that was this one right here, the 11 volts that drew 6 milliamps. The reason I removed it was because the 6 milliamps at 10.7 and then another 6 milliamps with no decimal at 11 caused a small but annoying flat spot. So I just decided to remove that data point to remove the confusion. But other than that, you can very definitely see that as the input voltage from the power supply goes from 0 volts up to where the Zener begins to conduct at about 8 volts for this 8.2 volt Zener, the voltage rises on the Zener with the power supply. And then almost immediately flattens out. It's not completely flat. There is a slow trend up. And on the input voltage versus current, from 0 volts up to the Zener voltage, basically no current flows. And then from that point on, it's quite a linear trend. Now, although you can use a simple Zener circuit like this to drive a load at a fairly constant voltage, the one thing that you have to understand is that in order for that voltage not to significantly change, the current through the Zener can't significantly change. So whatever the current is that is flowing through the Zener, the current that's being drawn by the load must be significantly smaller to not affect the voltage of the Zener. That makes the Zener voltage regulators kind of poor from a regulation standpoint, because as the load changes, so will the voltage. However, where Zeners are frequently used is as a stable voltage reference, because if you can pass a consistent current through the Zener circuit, you'll get a very stable voltage that you can compare to other things.